Hello, Chem 112. This is Virginia here with a new edition of a practice exam 2. So now that we have our 4 midterm exam format, the distribution of topics changed a little bit, and so this one has the newer version of how the problems are going to be divided up. Okay, and if you've used the 2B and 2A videos, I marked there which problems don't apply anymore. So we're going to go through this exam. And so I want you all to also be working through the problems too. So your paper, your pencil, your Chem 112 approved calculator, and that hardworking spirit, and we can do this. Okay, so let's go ahead and get into it. We're going to start with 5 kind of more rapid fire questions. Okay, so I have those all here, and we should be able to get through these ones pretty quickly. So here, the first one says, if the reaction quotient is larger than the equilibrium constant, the reaction will proceed in which direction? Okay, so our Q value is calculated the same way as our KEQ value, where it's our products to our coefficients divided by reactants to their coefficients. But here we can put in any type of concentrations. They don't have to be specific to equilibrium. And so I always think of equilibrium as kind of our destination. We're always moving toward equilibrium. And Q just tells us where we are in relation to that KEQ. Okay, so if we know where we are, we know where we're trying to go, we can figure out which direction we need to proceed. So, if Q is greater than KEQ, that must mean our numerator is big. We have too many products. And so, if we have too many products, we're going to have to proceed in the reverse direction to use some of those up to make more reactants until we reach the ratio of KEQ. Okay, so here we're going to shift to the left. Okay. For number 2, it says exothermic reactions are always exergonic. So exothermic is our negative delta H, and exergonic is our negative delta G. We can relate delta G and delta H together with our favorite thermodynamics equation. And so even if we have a negative delta H, if we end up with a really big positive minus T delta S term, then the delta G won't end up being negative. Okay, so since delta G is a combination of enthalpy and entropy, this statement's going to be false. Okay, so for number 3, it says if KEQ is greater than 1, delta G standard must be blank. Okay, so here I've written the equation for relating delta G standard and KEQ together. And if you'd like, you can plug in a number that's greater than 1 into this equation and see what sign you get on your delta G standard. Or you can think KEQ greater than 1 is going to be products favored. And if products are favored, that tells me the forward direction must be favored. And our delta G standard then is going to be negative. Okay, for number 4, we have Todd dissolving sodium hydroxide in water and feeling the bottle get really hot. So what this really hot tells me is that the reaction must be giving off heat. And so if heat is exiting our reaction, we're going to have an exothermic process going on. If we felt it get cold, then that would be endothermic. Okay, so then for number 5, it says when Q is less than KEQ, delta G must be what? Okay, so again, our Q is our products over reactants. And if Q is less than KEQ, we must instead have a too big of a numerator this time, or I'm sorry, denominator this time. We're dividing by too big of a number. And so we have too many reactants. And so we need to use some of those up and make more products. So our reaction is going to go in the forward direction to the right. And moving in the forward direction is going to be spontaneous, and that's going to have a negative delta G. Okay, so now we'll have 20 kind of longer problems to go through. Okay, so, sorry about the erasing. Here, for number 6, they're asking us which graph corresponds to a reaction reaching equilibrium. Okay. And so equilibrium, we know, is when the rate forward is equal to the reverse rate. And so when this happens, it's going to look like our concentrations stop changing. So there's no net change. They're going forward and backward at equal rates. So it looks like nothing's changing. And so initially what we'll have is some change and then it'll level out. And the scenario where that happens is here in graph A. And you can play with these graphs in the ebook in the ammonia synthesis app. And you can change your conditions and see how eventually everything levels out. Okay, so here with number 7, we have the oxidation of sugar, something we do all the time. And they want us to figure out how much work this reaction can do at body temperature. And so they gave us body temperature in Celsius, and I'm just going to right away convert it to Kelvin, because we're always trying to work in Kelvin. Okay, so when they're asking us how much work something's going to do, they're really asking us for delta G. And we know we can figure out delta G with our delta H and delta S values for the reaction. Okay. The one thing you'll want to be careful about when using this equation is that entropy and enthalpy are always given with different units. The delta H has kilojoules in it, and delta S has joules in it. And so what I'm going to do is convert my delta S value into kilojoules instead. And that way the delta G that I calculate will pop out in terms of kilojoules per mole, which is what the answer choices are written as. Okay, so we can go ahead and plug into this equation. We'll have delta G equal to minus 2573 kilojoules per mole for our enthalpy, minus our temperature in Kelvin, times our delta S in the proper units. Okay, and then this we can just enter into our calculators and see what comes out. And that value ends up being negative 2874 kilojoules per mole. And so that's saying that's how much energy is released, and so it can do a total of 2874 kilojoules per mole of work. Okay, so when we say something is doing that much work, the negative sign is kind of implied in our phrasing instead of explicitly written there. Okay, so it's okay to pick a positive number here. And I guess for that, if you had a positive delta G instead, we would say that 2874 kilojoules per mole of work are required to make this reaction happen. Okay, so the sign is sort of implied in our phrasing. Okay, so here we're doing more sugar combustion, and they want us to figure out what's going on. Okay, so here they say we have this combustion, and even if you don't quite remember the demo, it's pretty cool. It smells bad, but it's cool. There's a flame that's formed, and what fire tells me is that it has a negative delta H. It's giving off a lot of energy in the form of heat. Okay, so we say combustions have a negative delta H. So then that eliminates already answer choices A and E. Okay, and so now we need to figure out what the delta S is. And for this, we're going to look at the phases in our reactants and then in our products. Okay, because we know for entropy, if our molecules are all at the same temperature, gases have a higher entropy, followed by the aqueous phase, and then the liquid phase, and then the solid phase. Okay, so here in our reaction we're starting with all solids, and we end up making some higher entropy phases in the gases. So that tells me we must have a positive delta S. Okay, so that eliminates option C. So now we need to figure out at what temperatures is our reaction spontaneous. So then we can say, I'm going to use my delta G equals delta H minus T delta S equation. What I'm looking for is when delta G is negative. So if I have a negative number for my delta H minus T, and a positive number for my delta S, it doesn't matter what this temperature is because we'll have something negative minus something that's positive. And that will always end up being negative. Okay. And so this will be spontaneous at all temperatures. And this kind of makes sense because a negative delta H is considered favorable, and a positive delta S is considered favorable. So we have both of those things working in our favor anyway. So it makes sense that it would always be spontaneous. Okay, so we use the information about it being a combustion to figure out that it must be giving off heat, negative delta H. And then we look at the phases on our reactants and products to figure out whether delta S is positive or negative. And then we use our delta G equation to figure out how temperature will change the will or won't change the spontaneity of our reaction. Okay, here we have